In this experiment, we shall observe the beats of sound waves produced by two tuning forks on resonance boxes, and we shall study the concept of wave interference. We shall use the NeuLog USB Bluetooth module and sound logger sensor. Connect the sound sensor to the BLT module. Turn on the BLT module by pressing the button on the module panel. Click on the NeuLog application icon to load the software and to run it. The software automatically identifies which sensors are connected to the computer. Install the B480 Hz tuning fork in one of the sound boxes and the C512 Hz tuning fork in the other. Place the two boxes on the table, creating an angle of about 90 degrees as seen in the picture. Practice producing sounds by hitting both tuning forks with the hammer, one after the other, as fast as possible. It is recommended to watch the video, sound waves, and musical instruments before watching this video. Click on the sensor icon and set the sensor range to wave. Click on the Run Experiment button to open the Experiment Setup Parameters window. Set the experiment duration to 150 milliseconds. Set the sampling rate to 2,000 samples per second. Strike your tuning forks equally hard one after the other, as fast as possible, and immediately press the record button. Sampling is done in real time, and the samples are sent to the computer according to the communication speed. We can zoom fit. We can export the experiment and save it as CSV file. We can add cursors and move them. The X and Y values of each cursor are displayed on the left. Move the cursors to include a complete envelope wave. On the left, you can see delta X, which is the time difference between these two cursors. In our experiment, delta X is 50 milliseconds. The wave frequency is equal 1 divided by T. So, the envelope frequency is equal to 20 Hz. Between the two cursors, we count 25 waves. So, the wave frequency is 500 Hz. Clear the cursors on the screen. Click on the FFT of A without DC and create a function 1 graph. The FFT, fast Fourier transform, function displays the constituent frequencies and their amplitudes of the measured signal. Function 1 graph displays the two waves that construct the modulated wave. Add cursors and move the left cursor to the peak on the left. Move the right cursor to the peak on the right. Change the display on the left to show the frequencies of function 1 graph. The frequency displayed on the left is 482 Hz. The frequency displayed on the right is 525 Hz. Sound waves from different sources interact with each other and produce a new wave, which is the sum of them. Wave interaction is called interference. A sound signal is sine signal according to the following formula. A sine 2 pi ft. A represents the amplitude, and f the frequency. The following trigonometry formula converts a sum of two sine waves to a product of two waves. We can look at the following product as a sine wave with the frequency equal to half of the sum of the frequencies, and with amplitude wave with the frequency equal to half of the difference of the frequencies. This is what we call a modulated signal. Challenge. A string instrument add to the string sound over tones and harmonies as described in the video, sound waves, and musical instruments. Repeat this experiment by playing two stings on a string instrument.